Hello, everybody. My name is Hartmut Kaiser. I'm a professor at Louisiana State University, and I would like to give you an update on HPX. We are very proud to be here. For us, as an academic institution, being part of HPSF is absolutely an honor. Mostly because it turns the ideas of some crazy academics that sit in South Louisiana into something viable and acceptable. So we are very, very happy to be here. What is HPX? Some of you might have heard it. Most of you might not have heard anything about it because it's a very low-level C++ library. We call it a C++ library for concurrency and parallelism. So whenever you have need in your application for high-level parallelism, high level of concurrency, HPX is a solution we provide you with. You can think of it as a very efficient threading implementation. And by saying that, if you have been dealing with hundreds or thousands or tens of thousands of threads on Linux, you know that these overheads, context switching overheads, are in the hundreds of microsecond range. With HPX, you get the same, but with 2 to 3 orders of magnitude less overheads, so in the hundreds of nanoseconds overhead. We have added several functional layers on top of that, which makes it that's actually the valuable part. A standards-conforming API. If you're a C++ programmer and you know the C++ library, you can directly start with HPX because the APIs are fully semantically and syntactically conforming to the standard library. So we expose everything related to parallelism and concurrency from the standard up to C++ 23. We provide one of the first full open source implementations of all the parallel algorithms in the standard library. You might have heard of those. But we add a lot of extensions to that, and that's where the essence is. Asynchronous execution of those algorithms, parallel range-based algorithms, just to name a few. A full set of senders receivers. You might have heard of senders receivers as the new kid on the block in C++ that has been added to C++ 26. Although implemented for older compiler versions, which is important. And that was what makes HPX actually special, is that we have extended all these APIs to distributed case. So you can use the same code to run local parallelism, distributed parallelism. You can run it on your laptop, you can run it on the exascale supercomputers. People call it an asynchronous many-task runtime system. So if you have heard that name, HPX is a distributed asynchronous many-task runtime system. Quite a mouthful of words, but it kind of covers what it is. So essentially a system that gives you parallelism on a very fine-grained and very efficient level. Quickly, history. I'm not going to go through that. You can read the slides. Very mature, 15, 16 years old, 50 releases, 500,000 lines of code, very liberal software license, and financed through a variety of governmental, industrial contracts, and so on over the years. The community consists out of hundreds of contributors from all over the world, 400, 500 forks currently, 30,000 commit to master. We have a very open governance model. The project management committee consists out of 7 members from 5 different organizations currently. We're very active in C++ standardization, and we align our work with the standard very closely. So not only implementing what the standard has defined, but also interacting with the standardization process to influence where things go in the future. NumFocus affiliate have been part of Google Summer of Code for years, so very successful there. Our alignment with HPSF, well, we just got accepted on the tag level as a established project. We are going through the process of joining the Linux Foundation to finalize that. We believe that HPX is one of those things that has been designed for HPC in mind. We have a very long history with national labs and with applications from national labs. We support all the leadership systems, are widely distributed. When you do, application development for these big systems, and those are 6 of the biggest systems we have today, from the labs and the Recon system. You have to deal with, on 6 machines, probably with 12 different programming models. And as a programmer, this is really a pain in the neck. So what we thought is, what we need is a solution in C++ that gives you one API for all of this, and that's what we have done. Now, Christian probably will come back and say, hey, why don't you use just Cocos, right? Solves all the problems. Well, we think Cocos has 3 problems we wanted to solve in addition to what Cocos can. First, asynchrony. We added a layer of asynchrony on top of Cocos. Second, a efficient parallelization on CPUs. Cocos currently uses OpenMP. Unfortunately, that doesn't work very well together in the same application with HPX, so we had to do something about it. And certainly the distributed case. So here's an example. One of our applications, it's called OctoTiger. Octo because it's an octree-based application. Tiger because, well, LSU Tigers, yay. It's an astrophysics application, which is a full 3D AMR multi-physics, multi-scale code sitting or implemented on top of HPX. Does white dwarf mergers, contact binary simulations, and so on and so on. And what this is using, and the reason why I'm showing that here is because we believe that HPX is a perfect fit for many projects that are actually already in HPSF or are about to join. And OctoTiger is a perfect example for one of those synergies that might evolve because it uses HPX and Cocos. And by the way, it's using a library which is called HPX Cocos, and I hope that the Linux Foundation will not come after us that we use Cocos in the name of that library, because it integrates HPX with Cocos in a sense, but we have to discuss that separately. And I want to show you just some glimpse in what we will explain more in the Thursday session. Just some examples. Runs full system run on NERSC Perlmutter, 6K nodes on Fugaku, 1,000 nodes on Frontier, 256 nodes on Venado, 2,000 nodes on El Capitan, and so on. And all these with the same code. Absolutely the same code, just recompiled. Uses high level of parallelism, high level of asynchrony. The other example I wanted to show, just because Michael just presented Chapel, is another synergy of possible synergy between projects, where we created a source-to-source translator compiler from the Chapel language to C++. And that C++ that is being generated uses HPX for its implementation. I'm not going into details just because of time constraints, but here is just an example that we can beat Chapel hands down, at least in certain cases in terms of performance, for some simple use cases at this point. A quick word about ecosystems, just to give you an idea that HPX is very, very widely used in various contexts, performance tools, performance portability, Flexi, Cocos, mass libraries have been ported to HPX. Compilers, we have our own OpenMP runtime. Packages, E4S, SPAC, VC package, CMake, and so on, you name it, and many, many other things. One of the things I want to highlight is that we're currently working on developing a CCCL backend sitting on top of HPX, essentially thrust on top of CPU architectures, which will enable the Grace architectures and use of thrust on Grace architectures. The 2 links I'm giving you there is a GitHub repository and the documentation page. And last but not least, we will talk more about these examples in our breakout session on Thursday, and I really would like to see many of you there. I'd be very interested in talking to people from HPC Toolkit, from MREX, from other projects already in HPSF, because I believe there's a lot of synergy and we can do a lot of good things together. Thank you so much.
So again, we have time for one quick question while we switch speakers. Is there any question? Yeah.
You mentioned these fairly specific architectures, and I was wondering, do you have to add new ones manually, and how long would that take, if so?
Sorry, I don't see you. I really would like to. Oh, okay. New architectures. Well, it's C++. 99.99% is C++, so it is immediately portable. For the threading implementation, there are 20 lines of assembly. So if really somebody comes up with something very specific, we can easily implement that very quickly. But the rest is there. Just as long as there's a C++ compiler that can handle things. Okay.
Thank you. Thanks again.